Hi, I'm Mark, and this video is going to be a quick introduction to the difficult part of 2013 free response question 2 from the AP Physics C Mechanics exam. So we're going to skip part A because it's pretty straightforward, but part B says, write but do not solve a differential equation that could be used to determine the speed v of the box as a function of time t. If you need to draw anything other than what you have shown in part A to assist in your solution, use the space below. So we don't need to draw anything, but this box is subject to a constant force applied by some agent that's not shown, and the force is F sub A. There's no friction between the box and the surface, but there is a drag force of magnitude kV. So the Newton's second law equation would be F net equals ma equals applied force minus force of drag. So for part B, we want to substitute in for a differential expression for acceleration. So we just write dv dt equals the applied force minus the drag force, which is a function of velocity. That should be enough to get the points for part B. Part C says find the terminal velocity of the box. So in that case, when it's at terminal velocity, then the acceleration will be 0, and so everything on the left will be 0, and it'll just be pretty straightforward as well. So that V equals FA over K. Part D is the most interesting part. This FA over K is going to show up again in part D, which is kind of nice that they had us do it before we did part D. In part D, it says use the differential equation from part B to derive the equation for the speed v of the box as a function of time t. Assume that v equals 0 at time t equals 0. So let me erase what I've got and we'll run through that. Okay, so here's what I ended up with before. I had Newton's second law, mdv dt equals the force applied minus kv, and my task is to find a velocity as a function of time function from this. I know that velocity as a function of time is equal to the integral of acceleration as a function of time. So therefore, I must be integrating something here. I can't integrate this expression as it's written because I've got two different differentials on the same side. So I need to rearrange this, separate the variables and rearrange it so that I have the function and its derivative on the same side. So I'll spare you the algebra. If you don't follow what I'm doing, mess with this for a second, but what you get is dv over force applied minus the drag force, negative kv, equals dt over m. So I want to integrate this, and they've given me bounds, so I'll just write the integral of everything, and what we're first going to do is look at the left side because it's more interesting, more challenging, and it's the part that your students, if they're concurrently in calculus AB, probably won't know for a while. So you may want to put this off till the end of the year. The right hand side is actually really easy. The integral of dt over m from 0 to t is just going to be t over m. So we'll come back to that in a moment. Well, I know that this left side looks like the integral of du over u. And I know what the indefinite integral of du over u is. It's on the integral table, and that's just ln u plus c. So what I want to do is do a u substitution here, because this is not u can stand for a function, and this is a function, and this is not as simple as it might seem. You can't just mess with this without considering the fact that u and its derivative are not obvious immediately. So if this is the function u, it's force applied minus kV, then du will equal, that's a constant so it goes away, negative k dv. So now since I want everything to look like this, I need to think about what dv is. dv is negative 1 over k du. That's a k. Sorry. So I need to put a negative 1 over k over here, and that will make this expression look like du over u. So I'm going to write that, negative 1 over k, 0 to v, dv over our u function, which is fa minus kv. So now I'm ready to integrate. I know that I've got the correct function and differential. I've got a constant here, so everything matches up, and I'm going to just run through the integral really quickly. So this will be ln u, so that means that this will equal negative 1 over k ln of fa minus kv minus ln of fa. And that will equal negative 1 over k ln of fa minus kv over ln of fa. So give me a second, let me erase that, and we'll show you the answer. Okay, so here I have what I ended up with a moment ago, and I know that that is equal to t over m. So I'll put my negative k over here, and then I have a little bit cleaner looking expression. Negative kt over m. Now we exponentiate everything because we have natural log here, and we get this on the left side and our exponential function here on the right side. This is negative kt over m. Now it's just a pretty straightforward process to solve for v, and that's just algebra, so I won't run through that, but what you end up getting is v equals fa over k. Remember, that's the value that we found for the terminal velocity, times 1 minus e to the negative kt over m. So if you think about this, so this is our answer, by the way, for part D. As t goes to infinity, e to the negative kt over m, that goes to 0. So this function actually becomes v equals fa over k after a long time, and that's what we predicted for the terminal velocity. So that's a really good evidence that the answer is correct. Thanks for watching. Remember, what one fool can learn, another can.